In this video, I want to go over this simulation in more detail. So first of all, here's the big picture. What we're trying to do is we're trying for now to ascertain that this, which is derived theoretically, is in fact a true statement. So let's go back for a second and say exactly what it is that we're doing. So here's what we're saying. We're saying we have a population of x's which is distributed according to xi is distributed normally around mu x with variance sigma squared, which we assume we know. And we say we have another population, yi, which is distributed according to mu y with the same variance sigma squared. That's what we're saying. Now, what we're interested in knowing is, okay, is it the case that mu x is actually equal to mu y? Is it true or is it not true? That's what we're coming from. How are we trying to figure that one out? Well, we're trying to say, okay, so let's say that we have n equal 89 samples from x and y both, right? So 89 from x, 89 from y. And now what we want to do is we want to compute mean of x minus mean of y. And that's kind of going to give us an idea of, okay, if this is kind of close to 0, that kind of suggests that mu x is equal to mu of y. If this is very far away from 0, then no. But of course we know that we need to put some kind of confidence interval around this guy. And we did that just with theory. And here's what things work out to. We say that if you have this confidence interval, which you construct every time you conduct the study, every time you measure 89 x's, 89 y's, you can compute the sample mean for x, sample mean from y, stuff like that. And then you can construct this confidence interval. And what we're saying is that 95% of the time, if you construct this interval, then mu x minus mu y is going to be in that confidence interval. So, okay, now what I want to do is I want to just check that this statement is true empirically. Now, of course, we just know that it's true mathematically in this case. In other cases, we will not know that. But now what I want to do is I just want to check that this statement is empirically true. So, okay, here's what I want to do. I want to say, I'll first set sigma, and I'll set n to be 89, stuff like that. And I'll set mu x and mu y to those values. So those are just example values. Of course, they could be different. We want to say, okay, so for this particular scenario where mu x is 9.5 and mu y is 10.1, and those parameters are the way they are, things are going to work. Or at least we're going to try and figure and make sure that they are going to work. Here I'll set SD to sigma, even though in lecture I said it's just like 1.0. It's nicer to always use parameters. So this is going to be this sigma. So, okay. Here's what I'm doing here. First, let's look at what I'm doing inside the loop, and then we'll look in more detail into the loop itself. So, the first thing I'm doing is I'm taking a sample from x and a sample from y. So what's the sample from x? Let me show you the sample from x from 1 to 10. So in fact, sample x contains 89 numbers, but I'm just looking at the first 10 of them. Looks like that. If I generate a new sample, I just ran this line, I can see that the values are different this time around. They're going to be different every time. It's the same for sample y. So now I've taken sample x, I've taken sample y, and what I want to do now is compute the difference between sample x and sample y, the sample means of x and y. This is what I'm doing. So I'm computing the difference between the sample means. This is this part of the formula. This is this guy. So, okay. Now what I want to do is I want to actually compute the confidence interval. So I'll compute the lower the lower bound and the upper bound here. They're not really bounds, but I'll call them lower and upper. So those are this guy and this guy. So the left bound and the right bound of the confidence interval. So, okay. Now I want to say, okay, so I've computed my particular samples, which are going to be new every time, and I've computed my confidence interval. Now I'll compute mu x minus mu y. Note that this is going to be always the same. It's always going to be minus 0.6, because that's the difference between mu x and mu y. Mu x and mu y are set. They do not change. Here's what I'm doing now. I'm computing this value, and then I'm putting it into difference and end. So let's look a little bit at this value. So what am I doing here? I'm saying difference is greater or equal than lower, and also this is what the double ampersand means. It means and difference is smaller or equal than upper. So what this says is difference is between lower and upper. So this guy, this whole thing is going to be true if difference is between lower and upper, and it's going to be false if difference is not between lower and upper. So in this case, let's look at what lower and upper are. They are like that. Difference is minus 0.6, which means that this thing is going to be true. Let's just give an example. So let me just temporarily change difference to be like, minus 0.1, for example. And in this case, this value is going to be false, because minus 0.1 is not between this guy and this guy. So, okay, let me restore the correct value of the difference. And here's what I want to do now. I want to just show you how I would be computing this lots of times. So let's say that I compute this once, and now the lower and the upper are always going to be different. So this time around, lower and upper are this. Let me compute it again. And this time around, lower and upper are going to be a little bit different. They're going to be like that. In fact, that's maybe even quite a substantial difference, right? So they're going to be different every time. Every time I obtain a new sample x and a new sample y, this guy is going to be different. What I want to know is, okay, so this guy is usually going to be true, because usually the true difference is going to be between lower and upper. Sometimes it's going to be false. What I'm interested in verifying is that the difference is going to be between lower and upper 95% of the time. So what I'm going to do, how I'm going to do it? Well, I'm going to create this guy, which is going to store all the different values of this guy. So every time I run this guy, every time I run this block of code, I'm going to record what value I got here. And the way I'm going to do it is I'm going to stick difference in interval into this guy. I'm going to append it to the end. So let me show you. Initially, this guy is just going to be null. This guy right now is true. So if I run this line, what happens is that this guy now becomes true. Let me run this block again. And this time around, I also included line 30. And now this guy became true, true. Let me run it again. And now this guy is going to be true, true, true. And this is going to go on like that. Mostly it's going to be true. Sometimes you'll get a false. So now what does this for loop do? This for loop basically repeats this whole thing 1,000 times. and every time it adds another value to this guy. So let's run the whole thing. So I'm highlighting everything, including setting this guy to be empty initially, and then it's going to grow every time we run this block inside the for loop. Great. So let's look at what this is. So this is 1,000 values. Mostly they're true, sometimes they're false. How many times are they true? Well, I can do that using the sum, as you can see in the previous video. 947. What's the proportion of the truths in the entire thing? Well, I can compute it using mean. Why is that? Well, because the mean is really just the sum divided by 1,000, which is the size. So this is going to be 0.947. This is about what we expected, because theoretically we'd expect that the true difference is going to be in this confidence interval 95% of the time. What we obtained is that it's going to be in there in this case, and of course this is just an estimate because we just ran it 1,000 times, not an infinite number of times. It's going to be 94.7 in this case. If we run it again, so let me run it for this many times, and this might take a while, I'll get a different number that's still going to be very close to 95%. Okay, I waited a while, and if you try to run it on your computer, it's going to take about a minute probably. So let me now try to compute the mean of real differences in it. And it's 95.092%.